Working with polynomials and continuing to work with polynomials, we will start to see some patterns that develop, and in doing so, we'll see the sum and difference of cubes. And we want to be able to recognize a perfect cube and find its cube root, and then, of course, factor the sum or difference of two cubes. Now, a perfect cube is the product of three identical factors. Now I have some examples here. So if we have 125a to the sixth, well, 125 is the same thing as 5 cubed. And a to the sixth is the same thing as a square cubed. So that could be rewritten as 5a squared raised to the third power, or cubed. And then working backwards, of course, you know that the cube goes to both the number and the variable, so that would equal 5 cubed times a squared cubed, which is going to get us our original answer. And the same goes for this other example where I have negative 64 cubed to the 12th. Well, negative 64 is actually negative 4 cubed. Negative 4 times negative 4 is 16. Then 16 times negative 4 would give me that negative 64. And then here, this cube to the fourth, remember our exponent rules, a power raised to a power, of course, is going to be multiplication. So that would be cube to the fourth times 3 is going to be cube to the 12th. So when we rewrite that, we could write that as negative 4 q to the fourth cubed. And that would be identifying a perfect cube. And, moving into this, at this level of your mathematical education, you should be able to identify perfect squares up to 13, 15 times 15, or even perfect cubes. And you have to remember that some of our perfect cubes that we're going to work with is 1 cubed is 1, 2 cubed is 8, or working backwards, right? 8 is actually 2 cubed. We want to be able to move back and forth over that relationship. 3 cubed is 27. 4 cubed is going to be 64. 5 cubed is going to be 125. At this point in time, you should be able to pick those 5 out immediately. And then a little bit more challenging might be 6 cubed, and that will come to 6 times 6 times 6, which is going to be 216, or even 7 cubed, which is going to be 7 times 7 times 7, which is 343. These two may be a little bit more challenging, but once you've used them a couple of times, you start to recognize them. But definitely you should be able to, identify those 5, because that's just some basic math skills there. So with that, we'll go to looking here at, the cube root of a perfect cube. And again, breaking this down, a cube root, again, we're looking for 3 identical factors. So this would be the same thing as the cubed root of 125 times a to the 6th, which is going to be cubed root of 125 times the cubed root of a to the 6th. And again, the cubed root of 5 cubed, there we go, it looks like 5 cubed is going to be 125. And then the cubed root of a squared to the third power. And there's a lot of radical exponent rules here that we can look at, but again, this tells me I'm looking for 3 identical factors. This tells me I have 3 5s in there. So the cubed root of 5 to the third is going to be 5, and the cubed root of a squared to the third is going to be a squared. So there is my cubed root of 125a to the 6th. So I'll go ahead and I'm going to break this next one down, and that is going to be the cubed root of negative 64 times the cubed root of m to the 15th times the cubed root of n to the third. Now, again, if I need to, let's see here, maybe I skipped a step in the last time. So the cubed root of negative 64 is going to be negative 4 times negative 4 times negative 4, okay? Which is 4 to the third. The cubed root of m to the 15th is going to be m to the 5th times m to the 5th times m to the 5th. And I'm just rewriting these into triples, or, that cube. And then the cubed root of n to the third would be the same thing as n times n times n. So there are those perfect identical factors. So here the cubed root of negative 64 turns out that my three identical factors are going to be negative 4 times m to the 5th times n, or negative 4 m to the 5th n. So there is my cube root of our original expression. So just working these through and getting a little bit of practice. We were looking for those multiples of 3 for perfect cubes. So here, going on to the sum of cubes. Now, the sum of cubes is an identity, and here is my identity, and it tells me that a cubed plus b cubed is going to equal the a plus b times a squared minus ab plus b squared. That's the identity. And to prove this identity, what I'm going to do is I'm just going to go ahead and I'm going to multiply a plus b times a squared minus ab plus b squared. And using the distributive property, right? I'm going to multiply a times everything in that parentheses, and multiply b times everything in that parentheses. So my first is going to be, see here, I'll do the distribution of the a in green. So I'm going to have a times a squared plus a times negative ab plus a times b squared. And then I'm going to have b, and I'll do b in purple, right? I'm going to have b times a squared plus b times negative ab plus b times b squared. And let's see here. When I simplify those, or if I write those out, looks like I have a cubed minus a squared b plus a b squared. And that was me multiplying these out. Now I'm going to multiply the other factors out. So it looks like I have a squared b minus ab squared plus b cubed. And when I combine those, and again here is a squared b minus, right, minus ab squared plus b cubed. So when I go ahead and combine like terms, well, these are going to cancel out to 0. These are going to cancel out to 0, and I'm just going to bring down my a cubed plus b cubed. And there we go. I was able to prove that identity by working through it. So in doing so, what we want to identify here is, in this example as we walk through it, hopefully we recognize that 64 is a perfect cube and k is a perfect cube. So if I rewrote those in this format, right here, I want to find a cube. 64 is going to be equal to 4 cubed and k to the ninth is going to be equal to k to the third cubed. So it looks like now I could say, well, a is equal to 4 and b is equal to k to the third. So in doing so, I would say, okay, 64 plus k to the ninth is going to be equal to, a is 4, b is k to the third, and I'm just filling these in, right? Maybe I should include those real quick. A plus b, a squared minus ab plus b squared. All right, so we said a was equal to 4, b was equal to k to the third, so I have a is 4 plus k to the third times a squared, which is going to be 4 squared minus a, so that is going to be 4, and b was k to the third plus k to the third squared, and then that becomes 4 plus k to the third, and then this becomes 4 squared is 16 minus 4k to the third plus, again using your exponent to raised to a power, is going to be k to the sixth. And there you go. Now we have the 64 plus k to the ninth, which was the sum of cubes, could be factored to that. That is my factored form of that cube. And we were able to just sort of do some substitution here by identifying what my a and b were, and then substituting them into my identity or formula, and then multiplying them out, and this is my factored form. Being able to factor polynomials, a huge skill that is critical when you're moving forward in the remainder of higher level math. We don't need a calculator, we need to be able to do some math skills. So now, recognizing the difference of cubes, now if you'll notice that the difference of cubes, we have a cube minus a cube minus a cube, and it's going to equal this. And it is going to be slightly different. We're going to prove this identity real quick, and we'll do it the exact same way we just did before. That I have a minus b, and then I'm going to multiply a minus b times a squared plus ab plus b squared, and I'm going to multiply this identity out to see if it's going to result in the a squared minus b squared as we did before with the sum of cubes. So multiplying a times all of this, I'm going to have a times a squared plus a times ab plus a times b squared, and then I'm also going to have negative b here, so that is going to be a negative b a squared minus b times ab minus b times b squared, and then simplifying that, doing my exponent rules. Remember, those are all those, so this is going to be a cubed plus a squared b plus a b squared minus a squared b minus a b squared minus b cubed. That's going to become 0, that's going to become 0, so I just bring down my a cubed minus b cubed, and there we go. We were able to prove that identity just by working backwards. So we're going to go ahead and do the same, populate this just like we did on the last example, and knowing that if I look at this, hopefully you recognize this is a cube and this is a cube, And 125 q to the 6 should be the same thing as cube to the 6 should be 5q to the second times 5q to the second times 5q to the second. So A is going to equal 5q to the second. Then we have r. R to the 6 is going to be the same thing as r squared times r squared times r squared. So B is going to be r squared. So when I do my substitution, I have 125 q to the 6th minus r to the 6th is going to be a plus b, sorry, a minus b, right, times a squared plus ab plus b squared. So we said that a is equal to 5q to the second, and b is equal to r squared. So I'm going to have 5q to the second minus r squared times 5q to the second squared plus 5q to the second times r squared plus r squared raised to the second power. So I have 5q squared minus r squared times, remember this goes to both of those, so that is going to be 5 squared, which is 25q to the 4th, plus 5q squared r squared plus r to the 4th, and there is my factored form of my original expression right here. So I was able to factor that as the difference of squares. Again, filling in the blanks, remembering, I will tell you that the last math class I took calculus a few years ago, and this was a flashcard that I had to make until I memorized what my factored form of the difference of cubes was. Once you remember one, there's only a small difference between the sum of cubes and the difference of cubes. So just, seeing here the difference of cubes, I have the difference of cubes, so here I have a difference, and the rest are positive. Factoring for practice. Whew, look at this. Looks like we, potentially in these examples, this looks like a cube, and this could be a cube. I have to think. My powers is 42 divisible by 3. I think so. I think that's 14, right? 14 times 3 is 42. So I'm going to be able to find a cube here. Looking over here at this example, this is going to be a perfect cube, and so is this. So breaking these down as we begin, I have, looking at x to the 3rd, y to the 6th, that is going to be the same thing as xy squared times xy squared times xy squared. Now remember, I was looking for 3 factors, right? 3 identical factors, and there they are. So a is going to be equal to xy squared, and then I'm going to have 27 z to the 42nd is going to be 3 times z to the 14th. 3 times z to the 14th times 3 times z to the 14th. And of course that means that b is going to be 3 times z to the 14th, because again, I was looking for 3 identical factors. 3 times 3 times 3 is 27, and z to the 14th times z to the 14th times z to the 14th should be z to the 42nd, using my exponent rules. When multiplying like bases, we add the exponents. So, knowing that, I have a plus b, because it is the sum of cubes, times a squared minus ab. Ooh, did I just get that right? Think so. Plus b squared. And we know that a is going to be x y squared plus b is going to be 3z to the 14th. And then we're going to have something squared. So remember, squared right there. We're going to have a, which is going to be xy squared, square it, minus a, which is xy squared. B times b is 3z to the 14th, times b, sorry, not times, plus b squared, which is going to be 3z to the 14th squared. And in doing so, we simplify that out, and that'll be xy squared plus 3z to the 14th times, remember when you're doing your exponents, right, that exponent goes to both of those. This exponent goes to both of those. So the new expression is going to be x squared y to the 4th minus 3x y squared z to the 14th plus 9z to the 28th. There you go. There's our factored form of that. What a doozy. In the big scheme of things, it's not a lot of math, but you do have to do a little bit of factoring, a little bit of multiplying, and a little bit, in this case, we really don't do a lot of adding and subtracting, except for when it comes to your exponents. And let's see here, we got one more example here where we have the difference of cubes. And okay, I've gone ahead and done a little bit of work here. And I was able to turn around and say we have the difference of cubes because t to the 12th is actually t to the 4th times t to the 4th times t to the 4th. So that means that factor I was looking for, so a is going to be t to the 4th. And then my b, I have r raised to the 3rd power s15. So that's the same thing as rs to the 5th times itself 3 times. So b is going to be rs to the 5th. So using my difference of cubes, I have a minus b multiplied by a squared plus ab plus b squared. So a, we said, was a to the 4th minus b, which was rs to the 5th power, and that is going to be multiplied by, or looking in the factors of, a squared plus a times b plus b squared. And now when I go to multiply all of that out, I have t to the 4th minus rs to the 5th times t to the 8th, right, power to a power, multiplying, plus t to the 4th rs to the 5th plus, remember, power raised to a power, so that is r to the 2nd s to the 10th. And there you go, that is the difference of cubes, the factored form of the difference of cubes. And just remember the sum and difference of cubes. We're looking for in that perfect cube is the product of these identical factors, 3 identical factors, and being able to recognize that perfect cube and find the cube root, and doing it for the factor and sum of 2 cubes. You can factor the sum or difference of 2 cubes by finding the cube root of each add-in and then substituting these values into the formula for the sum and difference of those 2 cubes. Just, you have to remember, for the sum we have is the same thing as a plus b, a squared minus ab plus b squared, and then you have the difference, and that is going to be a minus b, a squared plus ab plus b squared. Now you'll notice there's very little difference between them. Here we have the sum and the difference. Here we have the sum and the difference. The only thing that's different, these 2 signs are going to be different. Otherwise, the rest of the formulas are the same. So when I have the sum, I have the sum, difference, sum. When I have a difference, I have the difference, sum, sum. So just filling in the blank and doing a little bit of multiplying and using your exponent rules. Get you a long way.